Welcome to the ADS University video tutorial series. Today we will go through the generation of a large-scale multi-stage unsteady simulation. In this video, we will cover the following topics. Considerations. Why full-wheel unsteady case generation is difficult. We will go through the workflow and how the ADS tool suite can be used to simplify the process. We'll examine some setup files, and we'll go through a sample execution. And finally, we'll wrap up with a summary. So what makes large-scale unsteady case generation difficult? Well, setup is time-consuming and error-prone because of the large MPI communication table, the large number of restart files that are needed, the large number of Leo setup files that are needed, and the long command line that is needed to execute the simulation. So if we take our 1.5 stage sample turbine that has 20 first vane passages, 30 first blade passages, and 30 second vane passages, we're talking about 80 setup files for a full wheel execution. Now that's big. So how does ADS help? Well, we do the manual labor for you by copying and multiplying the restart files, generating the complex MPI table and setup files, and finally creating a Leo execution batch file to execute code Leo. We start with ADS-fcool, taking in a setup file and converged steady-state restart files. It will then produce a Leo setup file and a restart file per passage per row. These will then get read into code Leo for execution. The ADS tool suite allows for multiple ways of executing this workflow. You can do it interactively through the workbench, or if you have a design system and wish to automate it, you can execute this through the command line. We will go through the process of executing it through the command line now. Let's take a look at a setup file. I have a fcool setup file already here called fcool.list. Let's open that up. So let me describe a little bit about fcool setup files. On the first line, you will notice that iChoice must be equal to 16 for multi-stage setup file generation. Also, you'll want to set iLeo, which is the 7th item on the first division, to 0. This will ensure that the Leo setup files and runleo.bat file is generated. In the second division, we have the number of restart files for this case. Since we are doing a 1.5 stage simulation, the number of rows is 3, so we place 3 here. The following divisions represent values for each row. If we look at the first row division, we will start with the first vane. Our first vane contains 20 passages and a steady-state restart file called row1x_pound.rest. Our second row division is the first blade, and that has 30 passages and a steady-state restart file of row2x_pound.rest. Our third row division has 30 passages and a steady-state result of row3x_pound.rest. This represents our second vane. If you wish to enable OH breakup for a row, you can set iSplit to 1 rather than -1. If there is clocking, you can set the clock value to the percentage clock needed for the row. Currently, there is no clocking in this simulation, so we set it to 0. Let's generate the setup files. As we look at the directory, you can see that I have already copied over the steady state restart files from our converged steady state simulation. We also have our fcool setup file, fcool.list. I will now go to the command line and make sure that I am in the execution directory. To run ADS fcool, you simply type ads-fcool, add the left caret, and then the fcool setup file. There are a lot of files that need to be generated, so this will take some time. So now ADS fcool is completed. Let's take a look at what was generated. We have our original files, and we also have 20 restart files for the first row, one for each passage. We also have 30 restart files for the first blade, or row 2x. And we also have 30 restart files for the second vane. Each of the restart files is an exact replica of the original steady state simulation. So on top of these 80 restart files that were generated, 80 .leo files were generated. We can see those here. It is important to look at the first Leo setup file, as it is the control simulation. It will control the simulation. You can see it has the number of iterations we had asked for. We set the I time to 3 for time accurate simulation. But the thing that it generates here is the MPI table with 84 boundary conditions that must be mapped. So you can see that the size of this MPI table is quite large. One thing to note when doing unsteady simulation is that at the end, the inner iterations and the iterations per cycle are placed here. If you would like to change them, you should change them now in order to set them to settings you are more comfortable with. So you can see our per cycle iteration is 4,500, which is equivalent to the number of iterations in total we are running. So we are running one full wheel. Let's close that out. The third thing that is generated is a execution file called runleo.bat. If we look at this, you can see that it is an MPI exec command that has multiple, that has all the command line settings you will need to execute this case. Because there are 80 setup files, this command line is quite long. Now to execute, you simply double-click on runleo.bat and the simulation should start. So when generating large-scale unsteady simulations, you'll prevent human error through automation using ADS fcool. Remember when setting up the fcool setup file to use iChoice16 for multi-stage setup, and iLeo set that to 0 to generate the setup files and runleo.bat file. If you need to change the simulation conditions, you can go into the in01.leo setup file and change them there. If you have further questions, please visit us at www.aerodynamicsolutions.com. You can check out the FAQ section or other ADS University video tutorials. If you do not find what you are looking for there, join the community and browse the forums. Good luck!